Greenhouse effect and global warming, looking specifically at the atmosphere. 3 definitions to know. Number 1, reflect. To reflect electromagnetic radiation is to have EMR bounce off the surface of an object. 2, absorb. To absorb electromagnetic radiation is to have an object suck in that EMR. And 3, emit. To emit electromagnetic radiation is after an object has sucked in the EMR, it will spit it back out either in the same form or in a different form. So we're going to look at how much EMR actually makes it to the surface of the Earth. So this Sankey diagram represents 100% of incoming solar radiation. Only 20% of it is going to be UV and X-ray, and that UV and X-ray EMR is absorbed by the ozone in our atmosphere. That's what protects us from getting severe sunburns. 30% of that incoming EMR is infrared, and that gets absorbed by the carbon dioxide and water in our atmosphere. There's something else that happens with that absorbed electromagnetic radiation. We'll talk about that a little bit later on. Finally, 50% of the original incoming intensity from the sun actually makes it to the surface of the planet. So 50% of the EMR that comes from the sun is actually absorbed by our Earth. We're going to spend some time looking at this Sankey diagram, which describes the path of electromagnetic radiation as it leaves the sun and heads to the surface of our planet. So if you notice here, we've got a incoming intensity and incoming intensity of 100%. And that represents, just like the previous slide, all of the electromagnetic energy that leaves the sun and heads towards our planet. Only 50% of that actually makes it to the surface of the Earth. Now, on the opposite end here, we have the electromagnetic radiation that is actually going to be absorbed by the Earth and then re-emitted by the Earth. So if 100% of the incoming intensity, only 50% of it gets absorbed by the Earth, notice that 106% of what was originally emitted by the sun is re-radiated back into space. And that's because, remember, Earth is a black body object. So as the Earth emits this energy, that energy will hit our atmosphere. And as it hits our atmosphere, the carbon dioxide, water molecules, and other greenhouse gases present in our atmosphere also absorbs that electromagnetic energy and re-emits that in all directions, including back to the surface of the Earth. And then we have this cycle that continues on and on again. And we call this a positive feedback loop, because as energy is absorbed by the Earth, more energy is emitted by the Earth. Therefore, more energy is emitted by the greenhouse gases. Therefore, more energy is emitted by the Earth. And we have a situation where the EMR that is emitted from the Earth just keeps on constantly increasing. And that, in general, is what the greenhouse effect is all about. We have some other places here where EMR is being reflected. Notice only 5% of the electromagnetic energy at this point is being reflected off the surface of the Earth. And radiation from the surface with no atmospheric absorption, that's another 5%. So, the full definition of the greenhouse effect. The greenhouse effect is defined as the condition where a planet emits infrared radiation, which in turn becomes absorbed by gas molecules in the atmosphere. These gas molecules will then, in turn, re-emit the infrared radiation in all directions, including back to the Earth, which is really important, thus warming the Earth's surface. There are 7 common greenhouse gases. Nitrogen dioxide, oxygen is actually a greenhouse gas. Not a great one, but it is one. Methane, the big culprit, carbon dioxide. Water, chlorofluorocarbons, otherwise known as CFCs, and ozone. So what I would like you to do is I would like you to take a field trip into the hallway outside of my classroom, and you will see that General Chemistry has already done a project about these greenhouse gases. I'd like you to go and write down the formula, the Lewis structure, which is the molecular structure, what the molecule looks like, and the name of each of these greenhouse gases in your notes. Here's another list of the greenhouse gases as before. This particular list tells you the greenhouse gas, the natural sources of that gas, and the human causes from that create these gases. So water is a greenhouse gas. We get that naturally from the evaporation of our oceans, rivers, lakes. Carbon dioxide, what nature does to create carbon dioxide, what humans do to create carbon dioxide, methane, and nitrous oxide. So again, the biggest culprit for the greenhouse effect currently is carbon dioxide, followed by a close second of methane. So here is the formal definition of a positive feedback loop. You saw this in the Sankey diagram as the absorbed energy of the Earth was re-emitted double what it came in as, and in turn created an elevated amount of heat that was trapped between the atmosphere and the surface of our planet. Definition of positive feedback loop is when a disturbance in a system causes the system to reach a new elevated state of equilibrium. The elevated state of equilibrium in our case is an increase in heat and temperature between the atmosphere and the Earth. A really good analogy for the positive feedback loop is when you play an instrument into a speaker. When you play an instrument into a speaker, such as a guitar, you're playing a note into the speaker, and the speaker plays that note back at the guitar, which in turn makes the guitar sound louder, which in turn makes the speaker sound louder, and you get an elevated noise level. That's very similar to what is happening with the greenhouse effect. As infrared radiation leaves the surface of the Earth, bounces off of the atmosphere, returns to the Earth as more energy is being put into the surface of the Earth, and you get this positive feedback where you have a creation of heat. So where was this positive feedback loop we were referring to in the Sankey diagram? Well, here it is. So as infrared energy reaches the surface of the Earth, that infrared energy is emitted back into the atmosphere. The atmosphere absorbs that infrared energy and re-emits it in all directions, including back to the surface, as more energy is coming to the surface of the Earth. So you create more and more and more heat, and here is the positive feedback. That's why we have an increase in global temperatures. So in order to counterbalance a positive feedback loop, we can have a negative feedback loop. And that's when a disturbance is created in the system, and the system readjusts to reach the same state of equilibrium at which it started, or at least a lower state of equilibrium. A good example of a negative feedback loop is when you exercise on a hot day, your body creates sweat, which returns the temperature back to normal. That's a negative feedback because that sweat is actually returning your body temperature to what it should have been at the very beginning. We need to introduce negative feedback loops into our ecosystem in order to bring the planet back to a lower state of equilibrium. Can you hypothesize one way of adding a negative feedback loop into that Sankey diagram on the third slide to begin to mitigate the greenhouse effect? So here is another way of looking at a positive feedback loop. We're creating more and more greenhouse gases as we burn more fossil fuels or add more cows to our ecosystem. That in turn causes the temperature to rise because of the positive feedback loop with the Earth's emission of infrared energy and thereby the atmosphere's emission of its infrared energy. And when you have a temperature rise, you have a sea level rise. Think about what can cause a sea level rise if you have a temperature rise. Then you have more water in your ecosystem. As you have more water in your ecosystem, you have a lower albedo effect. And we talked about albedo effect on Friday. Why would a lower albedo effect be created if you have more water? Think about that. If you have a lower albedo effect, you have more absorbed infrared energy. If you have more absorbed infrared energy, well, you have more or a higher temperature. You have a higher temperature, you have higher sea level rise, so on and so forth, and you've got this positive feedback loop. Here's a second positive feedback loop. If you have more absorbed infrared energy, more carbon dioxide is not dissolved in the oceans. And what happens there is if you don't have carbon dioxide that is dissolved in the ocean, then you have an acidification of the oceans. And that's how we have a decrease in shellfish and coral reefs currently happening on our planet. And if you have a higher temperature in the oceans, which can also be caused by more CO2 not being dissolved in the oceans, then again, the CO2 goes back up into the atmosphere and you have more greenhouse gases, therefore an enhanced greenhouse effect. So think about what could cause a rise in the sea levels to create more H2O. I'll give you a hint. Think about Antarctica and the North Pole. So we talked a lot about the atmosphere absorbing the infrared radiation. We're going to look at why that happens in just a second, and then we're going to look at some absorption spectra for different greenhouse gases so we can see which greenhouse gases actually absorb and emit the most and what type of EMR. So here we have a simulation where we've got different types of greenhouse gases and their molecular structure. Here's carbon monoxide, not the most common greenhouse gas, but it's on the simulation. Nitrogen gas, oxygen gas. Then here's the main culprits of global warming: carbon dioxide, water, nitrogen dioxide, ozone. Let's start with carbon dioxide. So if I shoot some infrared EMR at this carbon dioxide molecule, watch what happens. You notice that some of the infrared photons are being absorbed by the carbon dioxide molecule and then re-emitting those infrared photons in all directions. If I change the type of photons being emitted by this source to visible, watch what happens. The visible light photons actually just continue passing right through the carbon dioxide molecule. And that's because those visible light photons have a shorter wavelength than the infrared. And if I go to ultraviolet, those photons have a wavelength that are even shorter still, and they manage to pass right through the carbon dioxide molecule. If I go down to microwave, because these photons have a little bit longer wavelength than even infrared, they tend to pass right through the carbon dioxide molecule. Infrared photons just happen to have the correct wavelength to be absorbed by that carbon dioxide molecule and then re-emitted in various directions. Each one of these greenhouse gases has its own distinct characteristics. For instance, water, watch what happens. Some of the photons get emitted with infrared and re-emitted. Watch what happens with visible light. Pretty much all pass straight through. Ultraviolet, pretty much pass straight through. Microwave, microwaves actually have, since they have a longer wavelength, they will actually be absorbed and re-emitted just like infrared. So carbon dioxide and water, by looking at the simulation, will be your biggest culprits of the greenhouse effect because they have the best ability to absorb and then re-emit infrared or longer wavelengths of EMR. So on the right here, we've got a Wien's diagram where you've got intensity on the y-axis and wavelength on the x-axis. And the red portion here represents the downgoing solar radiation or energy that is produced from the sun heading towards our planet. On the right-hand side, we've got the upgoing thermal radiation, so from our planet into our atmosphere. And if you see here, the majority of that thermal radiation is in the form of infrared energy or photons that have a wavelength of 10 to the negative fifth. If I draw my attention downwards, I see that I can separate out the absorption in terms of different greenhouse gases. So what this says here is that water vapor will actually absorb infrared electromagnetic energy along with short and long wave infrared, some visible. No real UV is actually absorbed or emitted by water vapor. Carbon dioxide, same way. The majority of the absorbed and emitted energy is infrared. Oxygen and ozone, notice over here, majority of the the electromagnetic energy is in the UV. And that, again, is why ozone is there to protect us from the harmful rays of the sun. Methane has a peak here in the infrared range. Nitrous oxide, created by automobiles. Again, infrared electromagnetic radiation absorbed and re-emitted. And then the Rayleigh scattering is something a little bit different. The Rayleigh scattering has to do with our atmosphere and its diffraction of the incoming light from the sun into various visible electromagnetic energy. And that's why you see this down here. And this we're going to talk about more when we get into the waves unit. But the big takeaway from this graph is that water, carbon dioxide, methane, a little bit oxygen and ozone, nitrous oxide, all of those greenhouse gases will absorb infrared photons and re-emit those in all directions, including down back towards the surface of the Earth, creating that positive feedback loop and therefore an increase in temperature on our planet.